Hello students, welcome back. We completed section 3. Now let's go to section 4, Quadratic Reciprocity. What is quadratic reciprocity? Is this identity right here. Let P and Q be distinct odd primes, then now let's increase the font so that you can read it. Can you read it? And can you appreciate its beauty? Make it even bigger? Okay, alright. Now, okay, you can clearly read it, but can you appreciate its beauty? It's a sheer beauty, yeah, but do you see that? Well, here we go. When a mathematician says something is beautiful, a mathematical equality is beautiful, usually we are looking for several ingredients. Number one, simplicity. In my opinion, that's the most important. Something really simple is equal to another thing that is very simple. Number two, not so obvious. It's not very obvious why those two are the same. So the simpler the better, that's number one. And the harder the better, that's number two. And then there's some other aspects too, like symmetry. Yeah, you can see symmetry, PQ, QP, those kind of things. P minus 1 over 2, Q minus 1 over 2, those kind of things. And then duality, this Legendre symbol, P over Q versus Euler criterion, A to the P minus 1 over 2 power, or Q minus 1 over 2 power. So duality is also visible. There are a lot of ingredients that makes this thing beautiful mathematically. As for the second aspect, why is it not so obvious? Let's see, it's not surprising you're looking at negative 1 to the certain power. After all, Legendre symbols take only two possible values, positive 1 or negative 1. So it's not surprising we are looking at negative 1 to the certain power. But if I multiply two Legendre symbols, negative 1 to the certain power, and then negative 1 to another power, why not add up those powers? Why do we have this multiplication? This goes completely against our common sense. And yet, it's here with all those simplicity and symmetry and duality, whatever. So it's a beautiful result. It's a sheer beauty. I hope you can appreciate these kind of things too. But of course, it's a major theorem, so it's going to be hard to prove. We need some preparations. Lemma 1 by Gauss. And then lemma 2, that 2 is by Gauss. And then after that we have a corollary. That's relatively minor compared with the others, but these are the kind of things we are going to do in section 4. Let's postpone corollary here, and let's just work on the way to get to this quadratic reciprocity law. First lemma says P is an odd prime and A and P are relative prime. Then the Legendre symbol A over P is determined by some mysterious quantity n, which is given by a number of elements of a certain set, so that the Legendre symbol A over P is negative 1 to the nth power. Well, there's no surprise we have negative 1 to the nth power because, after all, Legendre symbols take only positive 1 or negative 1. So negative 1 to a certain power, that's to be expected. But why this n, and what is this n? Let's scrutinize it. N is a number of elements of a certain finite set, and that set is coming from a set of positive integers less than p over 2. You see, we have these positive numbers, positive integers, 1, 2, 3, 4, and so on and so forth, up to p minus 1 over 2. Next integer, p plus 1 over 2, exceeds p over 2, so that covered everything. And how many are there? Of course, p minus 1 over 2. Okay, but not all of them will qualify. We need an additional condition. Divide Ka by P, and Q for quotient, R for remainder, and the remainder has to be greater than p over 2. That's the condition here. That's the main condition. Remember, this is remainder. So if I divide by p, then p has to be greater than or equal to 0 and less than p. But here we have serious restriction. If remainder is close to 0, that's out. Less than p over 2, less than or equal to p over 2, then that's out. It has to be greater than p over 2. And then count those, and then there are n such elements. Then we get -1 to the nth power. And that's the first lemma. And here, this n value was given by the number of elements and counting. So the proof technique may have something to do with counting as well. Keep that in your mind. Yes, indeed. We're going to use counting as our main tool. Well, we have several other tools too, but one of the main tools is counting. Next, Gauss lemma number 2. P is an odd prime, yes, before, and this time p is also an odd integer, and not divisible by p, and that part is common as a matter of fact, because previously we had a and p are relative prime, but that's congruent to a is non-zero to p. I mean, did I say congruent? Sorry about that. That's equivalent to, logically equivalent to, a is non-zero mod p, and also p does not divide a. Yeah. A is not divisible by p, and this thing, a and p are relative prime, those two are equivalent. They mean the same thing. I can rewrite this thing into p does not divide a like this. As long as p is prime, p does not divide a, and a and p are relative prime, and a is non-zero mod p, those three things are equivalent. They're the same. And depending upon which is more convenient, we use one over the other. So, the second condition here, no surprise, but a is an odd integer. That's an additional restriction. What difference does it make? Well, that's something to think about. It's an odd integer. And then what do we have here? A over p is -1 to the summation. Oh, I need bigger font. So -1 to the n power here, which I just highlighted in brown, versus -1 to the summation power. So how are they related? Well, look at the summation, and this is not a Legendre symbol. This is floor function, the greatest integer of this fraction. Ka divided by p is a rational number, so if you take decimal expression, you may have, say, 6.71 whatever. And the floor function, the greatest integer function, brings down to 6. If you have 8 point something something, then bring it down to 8. If you have 17 point something something, bring it down to 17. If you have -5 point something something, then bring it down to -6. But in this case, you don't have to worry about negative integers or positive here. And then take that summation from case running 1 to p minus 1 over 2. Whew, complicated summation. And does it have anything to do with this n? Yes, indeed. We have to prove that. It'll turn out this n and the summation are congruent modulo 2. Not equal, but congruent modulo 2. So that if one is even, the other is also even. And one is odd, then the other is also odd. And vice versa. Therefore, -1 to that power is the same either way. And then an additional restriction, odd integer. How does that contribute? That's something to think about. And then using those, we're going to prove the quadratic reciprocity law. It's going to be a long walk, so we're going to use several videos on it. And I'm not going to write any exam problems or any homework problems or anything like that, anything directly related to this, because this is going to be a major accomplishment by itself. And one can argue this is one of the biggest accomplishments in this entire course, if not the biggest. So what we're going to do is go through all those and then put a period on it, maybe an exclamation mark on it, maybe several exclamation mark on it, and then we're going to move on. Yeah, we did it. So that's something we're going to start in the next video, going into all those proofs for lemmas 1 and 2 and this theorem. What we're going to do right now is the corollary. Using this, let's prove these for, let P and Q be distinct odd primes, then Legendre symbols P over Q and Q over P are the same. That is, they are both positive 1 or both negative 1 if P is congruent to 1 or Q is congruent to 1 mod 4. In other words, either one of them is a prime number of 4k plus 1 type. Remember, there are two types of odd prime numbers, 4k plus 1 type and 4k plus 3 type. Remember that? We started discussing those associated to distribution of prime numbers way back in lesson 4, and then over there we proved there are infinitely many prime numbers. Actually, that was done in lesson 3, and then infinitely many primes of the form 4k plus 3, we did it in lesson 4. And then in section 3, we proved there are infinitely many primes of the form 4k plus 1 as well. And furthermore, we have these relations associated to Legendre symbols. Strange, but interesting. And we're going to utilize this quadratic reciprocity law. I think I have to keep this font bigger permanently because I have to work out this power. Okay, let's go ahead. PQ and QP is the same if either one of them is congruent 1 mod 4, and then they have opposite if both are congruent to 3 mod 4, and we covered everything, you see. Either one of them is tail, both are head, kind of like that. We have 4 possible choices, PQ and mod 1 mod 3. Okay, first case, if P is congruent 1 mod 4, 4i plus 1, or Q is congruent 1 mod 4, 4j plus 1, in that case we have this computation directly from quadratic reciprocity law. Put it into this computation, what do you get? 4i plus 1 and then minus 1 divided by 2, we get 2i power. So negative 1 to the even power, so that's positive 1, and then whatever power, doesn't matter, we get 1. What if Q is 4j plus 1? Exactly the same thing going on to Q part. In the end the same, negative 1 to the even power to whatever power, we get 1. So, product is 1, so they have to have the same sign, and we can take only positive or negative 1, so they must be either both positive 1 or both negative 1. They must be the same. How about the second statement? If both are 4i plus 3 and 4j plus 3, both are congruent to 3 mod 4, then again I can put both of them into this quadratic reciprocity law and do this computation like this. Can you read all this? 4i plus 3 minus 1 over 2 to simplify into 2i plus 1. 4j plus 3 minus 1 over 2 simplify into 2j plus 1. Both are odd. And then we have product, but we can take first power and the second power later. And negative 1 to the odd power is negative 1. And then to the odd power again, still negative 1. So product is negative 1, that means they have to have opposite signs. So one positive 1 and then negative 1, one negative 1 and then positive 1, either way. That completes the proof. So we completed the corollary, but we didn't start the main theorem. That's something we are going to start in the next several videos.